Welcome everybody to today's colloquium, and it's a great pleasure to have Professor Andrei Geim here, and he got his degree from Russia, from Moscow University, from Czechoslovakia, and then he had a postdoc career in Europe, in the Netherlands and in England. And is now the Langworthy and Royal Society anniversary professor at the University of Manchester. And he's also director for the Center of Mesoscience and Nanotechnology. So that's the formal thing, you know. But you all know that we physicists, we are not like rock stars. You know, we don't make it really into public life. But few physicists actually do, and Professor Geim is one of them. So he's actually the one who made the frog fly. I'm sure you've all seen the pictures. For that he was actually awarded a very famous prize. You know, so awarded the, let's see if I get the year of that prize is the Ig Nobel Prize in 2006, was it, or something like that? So that's one thing that makes him very special. The other thing that makes him very special is also this thing that lots of us have looked at these green reptiles that creep up walls, the geckos. And lots of us presumably thought, how do they do it? And, you know, Professor Geim presumably also asked, how do they do it? But he also said, you know, if this guy can do it, I can also do it. So he invented the gecko tape that is a hot thing in the science of adhesives. But it's of course not that has brought him here. What has brought him here is one of the most exciting developments in material and condensed matter physics in the last 20 or so years. And you all know what I'm talking about. It's a real pleasure to welcome the discoverer of the magic flat carbon. Please.
Thank you. You persuaded me that being a rock star is very bad. I always thought so. Yeah, and I saw graphene only 5 years old rather than 20, but it doesn't matter. Anyway, okay. Thanks a lot and pleasure to be here. So in the next 40-45 minutes, what I'm going to try to persuade you that graphene is a very interesting system. I know some people here working on graphene, but okay, maybe more will start working. There are plenty of things to be discovered. Let me start with a simple observation, okay? All materials and objects, if you look around yourself, in the universe are generally three-dimensional. Of course, we know low-dimensional systems. They are low-dimensional with respect to certain properties, but with respect to other properties, they're three-dimensional. And with respect to crystallography, everything is three-dimensional. There are no objects which are one atom thick or crystals which are one atom thick and floating and flying around. So why it is so? There are many reasons for that, but probably the most fundamental one is that you can't grow low-dimensional objects. This movie is supposed to illustrate what's going on if you put carbon atoms in a black box and hit this black box enough in order to allow coalescence of the atom. They start moving around. Growth means high temperature, and high temperature, as you know, means violent vibrations. The bigger the crystals grow, the more violent vibrations are. You know this from Mermin-Wagner theorem, and essentially everything breaks bonds. So to minimize those vibrations, everything, okay, try to merge in three-dimensional form. So you can't grow more than nanometer scale crystals, probably. For the case of, I can't believe it, it's my computer, it happens, I stopped showing this movie, it happens for the second time in the row, I'm sorry, but it happened before, and it's probably somehow related to the screen. And the only possibility I know to end it is to end like this one. I spent 5 minutes a week ago or 2 weeks ago trying to press all buttons, including Ctrl-Alt-Del, and it didn't work. So okay. I don't know what's happening. So the idea is essentially that low-dimensional objects are completely out of this world because of many reasons. One reason is probably you can't see them, of course, but another reason is fundamental, as I explained, is that temperature doesn't allow growth. If you find out a way to grow at low temperatures, maybe you are lucky and you can grow materials, otherwise you are limited to very small pieces. For the case of graphene, people did make very specific calculations. Say diamond and carbon, and graphite are very popular materials, so no surprisingly that people previously make calculations about stability of carbon in different configuration, and what they found out that only small sort of 20 atoms molecules are thermodynamically stable. After that everything goes into 3D shapes, more stable, and if you go further, everything goes, bucketballs, carbon nanotubes, and so on, until you reach numbers something like let me go to this slide immediately. Something like 24,000 atoms, and after that configuration flat sheet becomes stable. So how to go through all those states instead of using growth, how to reach this stable flat state. So far only the largest hydrocarbon I know was a flat molecule like that, and it was only 222 atoms. Anything bigger than that was impossible. Can we think about something to get to larger things? It's not concerns only graphene, not carbon atoms, but all various different compounds. So one can think, okay, if it's forbidden to grow, we're humans, we can think something smarter, and this something smarter, okay, let's assume that you get a three-dimensional crystal, have a very tiny tweezers, and pull by tweezers a single atomic plane. On the surface of this, it looks like a crazy idea how to do this, okay, how there are no that sort of tweezers to extract individual atomic planes, but if you think a little bit more about that, that's the way was starting point somewhere around 10 years ago, which I was doing for quite some time, is that we know such things like epitaxial growth. There is a number of different substances which can be grown epitaxially, and a monolayer grown on top of other layer is a part of three-dimensional crystal, is important not only to give a direction of growth, but it's also important to quench those violent thermal vibrations. The interaction between the layer and the substrate quenches, allows this growth go beyond moment violence area. So what? If we know this sort of systems, the next step conceptually is very simple. You chemically age substrate. It has been done by sort of 100 angstrom thick materials like silicon nitride and amorphous carbon. So we thought to do the same with different materials, and we shopped around. People do grow monolayers on various substances, including graphitic monolayers, but when you try to find something, it's really hard. This is nearly all the references before, and not really easy to get materials like that. So the poor man approach, okay, like you don't know what to do, you levitate a frog. So in this case we thought, okay, we can't do by etching, can't we do something else? Exactly as I told you, pull out individual atomic planes. It's not as difficult with hindsight. So what you do, you take a bulk graphite sample and start chopping it like a butcher into thinner flakes, and you can really easy directly go into something like 30-100 layers. People before and after us made these sort of observations. What we did actually went further. You probably see here subtle contrast because light's okay, a little bit too bright, okay, but there is a single layer, what you can see, single layer 1 millimeter across. In this case it's deposited on silicon wafer. You can deposit those individual instructed layers on anything what you want. The step from here to here was not trivial, but this is history. The final result is we have this sort of layer. So what surprisingly, when you really know something that it's worth studying, then you can do plenty of tricks. A couple of years later, after extracting, we thought, why we're wasting material? Let's take graphite and extract not a single flake, but plenty of those. What you have to do is a trivial equipment. People, experimentalists, know that it exists practically in any lab. You have ultrasonic bars, you sonicate graphite in these bars for a few hours, then centrifuge, and what you end up? You end up with a solution or suspension of floating, mostly monolayer graphite flakes, which is graphene definition of graphene, mostly single layers. It's stable, it's solution of graphene if you wish. Surprisingly, okay, there was very close work to this done, but surprisingly no one did make this, okay, as I tell, 15 of 1 day step from graphite to graphene before. So lately it took 5 years, but it's interesting how these ideas coming back, and recently this what I started with has been realized, okay. Substrate was etched, and initially in 2009 3 groups have shown graphene on different surfaces, and it turned out, no one could predict it, turned out very high quality graphene, essentially obtained by poisoning of nickel and copper surfaces, and it took another half a year before people have shown sort of 1 meter in diameter graphene wafers. It's not a wafer, it's on some plastic substrate, but it's 1 or 2 layers of graphene have been plotted. So essentially from very tiny flakes of graphite you go and you see it's developed extremely quickly. It's not only graphene. I always put this transparency. It's not only graphene. There are many other layered materials. Already in 2005, we have shown that you can do the same trick with boron nitride, some dichalcogenides, and you can, of course, deal with 2, 3, 4 layers and so on. So the message to take away from this part, actually boron nitride is now coming really into place, becoming nearly as popular as graphene. So the message to take away that there is a new kind of material exists. It's essentially two-dimensional crystal objects. Of course, atomic planes were known since days of X-ray crystallography. The important part was to isolate, to study, and probably the most important part was to prove that those materials are worth studying. And it's not only graphene, we can do the same trick with lead materials, and probably not even lead materials as strong as you have strong bonds, ionic or covalent bonds. You can grow on other materials, single layers, and then etch away as I described. So plenty of stuff to be discovered. there. So I'm talking about graphene. It's in the title of my talk. So what's so special about graphene? Over the last 5 years, we learned that graphene has plenty of superlatives. Okay, of course, you can't imagine any thinner material than 1 atom thick. It has been measured that it's a very strong material, approaches theoretical limit. It's the stiffest material. We know it's stiffer than diamond. It's stretchable at the same time by nearly 20% elastically. Shows record thermal conductivity. It allows currents 1,000,000 times larger than copper allows at room temperature. It shows excellent electronic properties, conducts electricity in the limit of no electrons, I will be talking about, and so on. So there are many others I can put in there. What people are now joking that the only thing is missing is that we need to show that it exhibits the high superconducting temperature in this material, otherwise it's all covered. So I contributed to I studied some of those subjects, contributed to the others. So what I'm going to do in the rest part of my talk is to try to pick up some particular interesting phenomena and illustrate this exclusively on the basis of results obtained by my group in Manchester. So let me start with mechanical properties. It's a very badly studied subject at the moment, and I just like to tell what we know that it's stiff and we know that it's strong. But how do we know that? So a few years ago, only a couple of years ago, we learned how to make suspended graphene. We got sort of 3 millimeter in diameter, several holes there, and those holes we can cover with graphene. Here you see graphene sheet in transmission electron microscopy, nothing here, a little bit folded and so on. Initially it was just to see this material. You can see it's crystal lattice quite clearly. Electron hits between the ring inside. Benzene ring goes through. When it hits the bond, it's slightly reflected. It's extremely weak contrast, essentially. If you put any other foreign atom on top of this, you can distinguish it reasonably easy. This is the case of oxygen or silicon, but you can distinguish even hydrogen or even a foreign carbon atom on top of this. This is what I'm going to tell about. This is about magnetic properties, and this is view from the top or from the bottom of a flake of graphene, a single layer of graphene, which is supported from this side, okay, here, and it stretches 5 or more microns away. It's 1 atom thick, and yeah, it covers all the area. So if you look through that length aspect ratio, it's like a piece of glass which extends over a few kilometers and covers a bridge. In addition, it's loaded with copper particles in this particular case, just happened, and in addition, you move it, and when you move nanomechanical system, its shock acceleration usually exceeds 10 to the 3,000 G. And still doesn't roll, still doesn't bend. So, okay, that's an observation which continues shocking me, because usually, according to thermodynamics, it should roll into a scroll, and it doesn't roll into a scroll. There are huge barriers we don't understand. We only know that stiffness helps. You can do it with FM more carefully, but this, okay, sort of qualitative observation, stiffness and strength of the material is really shocking. Not much is known yet about mechanical and thermodynamic properties of graphene as a freestanding object. The biggest subject, which is most mature subject, is actually electronic properties of graphene, and it will take most of my talk. So in the very first studies we did the following. We not only observe those flakes that you can isolate. It's not that important. More important that we we make devices out of those flakes and start measuring, okay, their properties, and eventual devices look like that. Many contacts, and you can measure hole voltage, you can put in magnetic field, different temperatures, resistivity, and so on. What we found in the very first work, that when you apply so-called gate voltage, a potential, to the substrate through a silicon oxide layer, you pump in electrons or you repel electrons out, and you see so-called ambipolar electric field effect, where resistivity rapidly goes down when you increase the number of electrons and goes up. The speed of this tells you about the quality of this material a lot, and field effect proved to be absolutely amazing tool to study physics in graphene. So we use this gate voltage as a routine tool to see what phenomena we in the very first work we found that electrons, actually, I don't want to give you such numbers like electron mobility and explain for those who do not know. So let me translate mobility directly in how far electrons go. So essentially, in this atomically thin sheet, which lies on a rough surface, which is covered with all sorts of absorbates, electrons shoot thousands and thousands of interatomic distances without scattering. So somehow these electrons are protected from external weather, so they can move without much hindrance on very long distances. Currently, and initially, it was sub-micron distances. We hope at room temperature it could be micron distances or even larger distances. When you get a high quality material, it immediately tells you that you can study a lot about this material. That's the latest result, where we try to improve quality even further. We suspended graphene on those fingers, and unfortunately it's essentially two probe measurements, but it's suspended in air and annealed at 1000 centigrades by current, so all absorbates and everything else goes off. And in this material we again observe this, okay, what I call ambipolar ambipolar field effect, and the curves look the same, but the scale 100 times different. So it's much higher quality in terms of mobility. We reach what is typical for gallium arsenide structures. We don't have any doping and etc. So, okay, how to explain it in a simpler term? If you apply magnetic field, you start seeing quantum oscillation is essentially in 100 Gauss. And not quite the Earth's magnetic field, but close to that, and you lift all degeneracy of all the level in the field of a weak permanent magnet, essentially. So quantization is extremely strong phenomenon. Particularly, I like the fact how sharp those peaks are. They, at low temperatures, at high temperatures, it's thermal broadening. At low temperatures, the peaks are extremely high. And if you translate this broadening in terms of the number of electrons per typical device, you get around one electron or one hole or one combined particle, which we later, I'll explain, called Dirac fermion in those devices. It's no inhomogeneity left in this device. So the message from this one, if we have a very high quality devices, we can really approach very critical regimes, which I'll describe a little bit later. So all these phenomena are essentially due to a structure of graphene, electronic structure of graphene, which is the next part of my talk. In the very first, our first and second paper, third paper, we start putting these devices in magnetic field and looking what's happening. We see plenty of oscillations, and from those oscillations, Shubnikov-de-Gas oscillations, we can find out effective mass, and from effective mass we can reconstruct the spectrum electronic spectrum in graphene. It looks not parabolic as usually, it looks linear spectrum, and in agreement with previous with developed series from many years before. In addition, when we put in quantized magnetic field, we see something unusual. It's not an electronic spectrum, it's linear, but it's also so-called quantum Hall effect. It's not trivial, but shifted by a factor of half. Usually for parabolic spectrum, you expect platters at integers. We see them at half integers, and combined with cyclotron studies, we know that energy in quantized is not normal energy for electrons. In addition, there is such system as bilayer graphene, and in this bilayer graphene the quantization is also different, and quantum Hall effect is different, and we know from combination of those measurements that quasi-particles in these two materials, graphene and its bilayer, described by those Hamiltonians, which is not the normal Schrödinger Hamiltonian, but those two. Let me just take a second and put a perspective. You know that there are two quantum Hall effects, okay, integer and fractional. One might argue that fractional quantum Hall effect is just integer quantum Hall effect for composite fermions, for quasi-particles called this way. In our case in graphene, we get two additional integer quantum Hall effects for the case of what we call massless Dirac fermions here and massive Dirac fermions in the case. I have no time to explain the origin of those massless particles, but it takes from the hexagonal lattice and how electron moves through this lattice around. So again, a perspective. This is our metal or semiconductor material science. What theorists especially, they toy with single equation. If it's material, the interaction with the crystal lattice is explained by effective constant, which is not the mass of free electron, but effective mass. The particle physicists and astrophysicists, they deal with a simple equation. Every old physics come on the top with additional terms and with interactions and so on. But that's essentially. It sounds sad that all physicists, okay, most of the physicists are restricted to studying consequences of these two equations. So graphene expands our sort of universe of possible equations by a factor of 2. First, it mimics this equation. It's mimicry, it's not exact. There is nothing relativistic about graphene. It just, okay, because mass goes to 0 because of this interaction of electron waves with honeycomb lattice, we get exact mimicry of ultra-relativistic particles. Effective mass goes to 0, and as in the case of ultra-relativistic particles, we get conical spectra. Instead of spin, we get additional degree of freedom, or index. It's index of two sublattices in graphene, red and blue, like spin up and down. It's red and green sublattices and massive Dirac fermions. They explain, okay, even more weird equation, which gives us sort of a basis to compare two materials and look for other phenomena. So where does all this lead to us? Obvious scenario is that we can now, within graphene, try to mimic those phenomena which are known in quantum physics but have never been seen there, and some of them I assume not to be possible to observe, but our condensed matter experiment allows this. One of those is Klein tunneling. Let me remind you that classical electrons, if they see a barrier, electrostatic barrier, they can't tunnel if the barrier is wide or high. In the case of ultra-relativistic particles, a consequence of Dirac equation that whatever barrier you construct, you can't localize your particle. It moves through the barrier with 100% probability, first found by Oscar Klein as a consequence of the Dirac equation. So what we expanded a little bit, the same formulas for the case of our particles in a couple of years after we start doing graphene, and in the last 2 years there are plenty of experimental observations of this Klein tunneling in material, and it's very important phenomenon. Many properties of graphene, like why you can't localize particles, why it's so difficult, why you can't make barrier, is based on this Klein tunneling phenomena. So another phenomenon which is actually unique for graphene as an electronic system is something what I like to tell you now. For those who are familiar with the physics of semiconductors, it's a typical case of zero-gap semiconductor. So what we can tune by electric field, we can reduce the number of electrons or reduce the number of the holes and come to this point which we call Dirac or neutrality point, and we expect here there would be no particles. The density of states goes to zero, so resistance of the system should shoot up and the system should become an insulator. Indeed, we reduce the number of holes, we reduce the number of electrons, and it shoots up. But what we have found already, in 5 years ago, that we found out that, it never goes to an insulator. It always remains metallic or metallic light. So it's not zero gap semiconductor, we called it zero gap semi-metal because it remains metallic even in the essentially in the absence of charge carriers. So those are initial data from 3 years ago, different devices, and this is minimum conductivity we observe in our devices. Now we have these million mobility devices I already mentioned, and it's still we go to one Dirac electron or Dirac hole, Dirac fermion, and it's still we single electron within 1 micron device with plenty still impurities present somehow provides the same conductivity as many of those. Theoretically, 1 electron should provide a conductivity even for 1 kilometer square piece of material. It's not conductance, it's conductivity, so it scales with parameters. So we called it here minimal metallic conductivity. I don't have time to explain this, but it's related to the absence of localization phenomena in this material, which in turn relates to the Klein phenomena we observe. But that's a matter of fact. Whatever you do with this material, you can't kill in large pieces, you can't kill its metallic state. Another phenomena is very fascinating. Essentially it's not observed yet experimentally, but we are looking forward to this. It's transparencies taken from Antonio Castroneta. So what we are looking for, our periodic table is limited something like by 110, 120 elements. Imagine that someone would create a very heavy nuclei with a charge 200. The question is whether we would have some stupid new material and so on. And this is Bohr model of periodic table, and it works fine for all our atoms, but if you really get a super heavy nuclei, then you have to take into account relativistic corrections, which are described by the coupling constant, and then it's called fall of electron on the charge center, and then the system becomes unstable. Where graphene comes from, in graphene the coupling is described by the same constant, but instead of speed of light you get interaction described by 300 times less than speed of light value, and you get all charged impurities in graphene become overcritical. It means that you can get all different sorts of phenomena related to screening and so on, and you can mimic this phenomena, which is known for 60 years of the fall on the center, but has never been observed. My next example is about, very simple, educational, didactic example. So one of those membranes I discussed before, we just cover in this way. So a gap of air, graphene layer by layer, graphene layer. What you see, the light shines from behind the screen, and you see this in a microscope, but essentially by a naked eye, because it would be the same. So the light goes through the air without impedance, and graphene absorbs. As you see a single layer crystal, which is essentially visible by naked eye, because it absorbs little, but actually surprisingly a lot, 2% or so of light. So between you and me there are billions and billions atoms, and light shines through here. A layer of carbon absorbs 2.3%. Nice to see single crystal by naked eye, but what you can do, you can analyze it spectroscopically, and this is our spectroscopic measurements, what's happening, and it's pretty boring, nearly flat spectra for all visible frequencies. 2.3% with very high accuracy and etc. What 2.3% means? It's rubbish. This is where theory comes into play. You compare this in terms of Joule losses, say how much light is absorbed as Joule losses, and you can deduce conductivity of this material at optical frequencies. Again, it turns out to be conductivity of the order of E squared over H, and this 2.3% actually then translates to quite meaningful number, which is pi times the fine structure constant, the real fine structure constant there. So in this experiment, essentially by naked eye, you see not only the material, the thinnest you can imagine, but you probe the fine structure constant. I try usually to trivialize as an experimentalist all the observation, and you can really think why it's happening, why fine structure constant is important, because in this experiment you probe interaction, coupling of light with relativistic light charges, and this coupling should be described, of course, by the coupling constant, and the coupling constant is also known as the fine structure constant. If you see, this is intuitive description of this experiment. My final example is that it's a bit about chemistry, I'm afraid. So coming back to this idea of graphene as a giant molecule, if it's a molecule, you can think not as a physicist but as a chemist and say, can I modify this molecule? And this was what we tried. We noticed that both surfaces are available. So it's sort of very unusual solid-state chemistry when you have two surfaces at once, and it's important to have those two, or you can consider this as a chemistry of giant macromolecules. So we expose graphene membranes to fluorine. This is the spectrum of normal graphene. This is the region we discussed before. Here there is some Van Hove singularity, because spectrum in graphene becomes non-linear. You expose this to fluorine, it becomes more transparent, and when you really expose it, it becomes completely transparent, and then you can guess that there is a gap. Valence and conduction bands start to absorb light at something like 3 eV. It's what we spent a lot of time on this, but I have no time to describe this one. So what we get here, a derivative of stoichiometric derivative of graphene, which we call fluorographene. You can consider it as a two-dimensional Teflon, because the formula is the same, and this is how, if you make many layers, we call it fluorographene paper, you can really see that this material, unlike graphene, is completely transparent, even if you stack plenty of those, and the color corresponds to the gap I described before, 3 EV. So the message to take away is that it brings, okay, cornucopia of new science. Most phenomena currently, okay, Klein tunneling, quantum Hall effects, and so on. It's all concentrated around electronic properties, but I think that optical, mechanical, chemical, for chemists of course, properties are equally fascinating. Okay. I know that most of people do not have nothing to do with applications, but maybe I spent a couple of transparencies just to give you a flavor what sort of applications we are talking about. 2 years ago it would be complete nonsense to speak about applications, but what happened during the 2 years, we got plenty of different techniques to get this material in bulk and in wafers, and the quality is approximately the same, slightly only less than what I described in our transport experiments. Okay, so because of these unique properties, people start thinking what's possible to do, and the first actually was probably first published in our paper 6 years ago. It was, what can we do with this material in terms of new transistors, because its electronic properties we studied first, because such high quality maybe translate in something new. The problem is this is saturation, this minimum conductivity I told you about but didn't explain. It really kills all transistor applications, because okay, you can't really pinch off the channel. If you put current, it always leaks through, it means heat and so on. Otherwise, material will be great. People and ourselves, what we are trying to open the gap in the material. One of the way I just described is fluorinization, to get another semiconducting material by chemical modification. Another one is by just confinement, quantum confinement, and we were reasonably successful demonstrating different transistors. The problem is that each transistor is different, and we really can't work on the scale less than 10 at the scale of few nanometers. It's really hard to make anything reproducible there. But what is fascinating, that the current the graphene sustains is about 1 microamp per atom. As I told you, copper or anything like that would immediately evaporate, and actually before you apply current would diffuse around. And this material is fantastically stable. So the dream, which was and still is, okay, is where we are now, and go to really by top-down approach to molecular electronics. If we can come with such accuracy devices, we're in business, but it remains a dream, okay, pushing many groups within the area. In progress, okay, you can think about not integral circuits where everything is made from graphene. You can think, okay, less ambitious is, why wouldn't we make individual transistors out of that? That's the standard device, and the point that it's limited, okay, resistivity at this point is not really important, as long as you can get reasonable on-off ratios, as on this picture. This was taken over by, I'm afraid to say, US military, which put a lot of money into several programs to make this happen. And last year, several groups demonstrated, okay, 100 gigahertz transistors in pretty pathetic graphene devices, I would say. Despite being pathetic, it still gives very high frequencies. And this is the wafer I was told was shown to President Obama as one of the achievements, of 5 biggest achievements of nanotechnology in recent years. Okay, it's probably not working member, and I'm not sure whether it's a federal offense to lie to your president. Okay, but essentially we all know that it's only a stepping stone, and we hope that this can be scaled to very high frequency transistors, individual transistors, which are really required for many applications. Okay. Unfortunately, where it all goes, it's less sort of grandeur applications. It's okay. This is a warehouse taken from Nature Nanotechnology website, where it's supposed that this is graphene in bags waiting to be shipped to somewhere. Actually, people are making conductive ink out of this. Why graphene? Because it's strong, it's lipophilic, it's highly conductive, and it's needed to be filled in plastic. So far, it's more or less flaky materials. Individual layers are important, not reached yet, because I told you already that chemistry very much matters, whether you do chemistry from one side or both sides are allowed to participate in reactions. And okay, monolayers are more strong than bilayers. They can't be cleaved against each other. So this goes pretty well, and people are looking into all sorts of applications. Let me skip this one, a company trading with saturable absorbers. What I like to point out, that sort of things we were thinking before, because it's reasonably transparent, 2.3%, and highly conductive. You can start thinking about, well, I can use it where for optoelectronics. Say this LCD projector or your computer screen inevitably use a material which is called ITO, indium tin oxide. It's expensive, it's rare material, and people are desperate to find a substitute. This is what we demonstrated as a proof of principle. Okay, a few years later, people are now, Samsung actually, driving this project. People are thinking about, at least very optimistic about touch screens and computer screens using graphene. We are not there yet. Transparency to ratio are probably just enough for computer screens and good enough for touch screens and so on. So we'll see where it goes. 1 year, so this is pilot production supposedly in Samsung. At Samsung, one of the applications I'm particularly enthusiastic and want to mention, because it comes from a Swedish group. Okay, they combine graphene with liquid, with polymer liquid light emitting diodes, and it turns out that those OLEDs and graphene turned out to be fortuitously a perfect match. So here to show LED with graphene electrodes, which shines both sides and produces logos of some Swedish institutes. Sorry, I don't remember which one. That looks very promising. So flexibility, of course, comes on top. People are talking about wall panels using this. So to finish this application part of my talk is to say that, okay, I'm really amazed that only after 5 years its applications are no longer wishful thinking there. We don't know the extent of those applications, but they're certainly coming online, and we, as I told, there is plenty of stuff to be found about all properties, not only graphene. We don't understand much, except maybe electronic properties, but other materials like boron nitride are still essentially untouched materials. Finally, I acknowledge all collaborators in this work. One of them is a Swede, Fred Shedin is a Swede, so it's a particular pleasure to acknowledge his contribution. Okay, thank you very much for your attention.
Thank you very much. Questions?
Well, the mechanical property, you show that single flake standing up.
Yeah.
How sure you are that there is no electrostatic charge in that?
Flake is conductive and it's on conductive electrode. Yeah, so I'm not sure about electrostatic charge, but okay, it stays for. If there would be electrostatic charge, it would be varying with time. Okay, so not only ourselves, but many people observe that. But there is no charge in effect. It's conductive material, essentially, very highly conductive material.
In the quantum Hall effect measurements, how precise is the quantization of the black holes?
If you refer to our measurements, okay, it's not very precise. It's okay. Well, I think we said it's 0.1%, maybe 10⁻⁵ or something like that. Okay, so there was another paper in collaboration. Our paper we moved to 10⁻⁸, I believe, in small flakes. But recently there was a sort of nice paper from a collaboration of British and again Swedish group, okay, in which people showed, I think, 10⁻⁻⁸ or something like that. It's not quite yet, but it's okay, less than a factor of 10 to the best measurements. And this is the very first the measurements, meteorological measurements made in London Meteorology Office and so on. But so there is a possibility, real possibility within a couple of years to compare the standards based on graphene and other semiconductor systems. That was an important development this year.
Can you tell us how Samsung is making those big sheets?
So it's it's the same idea I try to advertise. It's chemical action. So essentially, okay, what you take there are many metals around. One of those metals is copper. You can use nickel. You can use titanium. And when you expose them to hydrocarbons at high temperature, the surface is poisoned and passivated. This is the process which kills your catalytic converters, because a very thin film of graphene actually grows on the surface. So you grow this film on say, on copper, then etch away. So etch away. Surprisingly, you don't need a monocrystal. Polycrystal is fine, okay, there are domain boundaries, but somehow by magic they do not play much role, and they etch away and transfer it to whatever surface you want.
So I have a question also, and that is that some time ago it was the news about the room temperature quantum Hall measurements. Which was very fascinating because it was room temperature, macroscopic quantum effect. What's the status of that now?
It's in a sense, let me see what I have. This transparency or not? Probably not. Okay. So essentially, okay, yeah, it's you observe at room temperature. Reasonable quantization, I think we claim 0.1% at room temperature. It's not a big news because the gaps which are important are sort of 1,000 Kelvin, 10,000 Kelvin. So actually it was surprised that you need to have such a huge magnetic field like 30 Tesla to see this. What we extended it recently extended it to capacitance measurements. In capacitance measurements, you really can probe the density of states. It's direct measure of the density of state. And we see the peak which generates by magnetic field at room temperature, something like 5, 6 Tesla at room temperature. So you see quantization in reasonable fields, sort of 5 Tesla, as I said, at room temperature. That's sort of really fascinating, because I think all quantum phenomena are at low temperatures, but yeah, 5 Tesla, big or small, I don't know, but the peak is clearly there.
No more questions? So then, we thank again.
Thank you.